Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of this semicircle that is inside this quarter circle. And in the second question, we'll find out the area of this green shape that is inside rectangle ABCD. So we'll start with the first question. So in the drawing, we have a quarter circle. AOB is a quarter circle. Inside, and we know that AO equals to 5 units in its length. AO is actually the radius of the quarter circle. So the radius of the quarter circle equals to 5 units in its length. And point O is the center of the quarter circle. And inside this quarter circle AOB, we have this semicircle. And our mission is to find out the area of this semicircle. So first of all, we'll define the center of this semicircle. This point is point C. So CD equals to CE. They are both the radii of this quarter circle. So we will define the radius of the quarter circle as x. So CD equals to x and CE also equals to x. They are both the radii of this semicircle. And we know that angle AOB equals to 90 degrees in its size. And point O is the center of this quarter circle. Here we will join points. First of all, we'll define the point of tendency of tangent BO with this semicircle. This point is point F. And we'll define the point of tendency of tangent AO with this semicircle. This point is point G. In the next step, we will join point C and F together by a straight line. CF is the radius of this semicircle that equals to x according to our definition. Here we can implement rule 1 because we have the radius CF of this semicircle that is drawn to point F, that is the point of tendency of tangent BO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius FC. If BO is perpendicular to FC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we will join points C and G together by a straight line. CG is of course the radius of this semicircle that is equals to x according to our definition. Again, we have the radius CG that is drawn to point G, that is the point of tendency of tangent AO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AO will be perpendicular to the radius GC. If AO is perpendicular to GC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So, by doing this construction, we created here quadrilateral CGFO. Inside quadrilateral CGFO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral CGFO, we have 4 right angles. And according to 5, any quadrilateral that has 4 right angles must be a left angle, if not a square. So we relate to quadrilateral CGFO as left angle because it has 4 right angles. But we also know that the opposite sides of a left angle are equal to each other. So left angle CGFO, side CG must be equal to the opposite side FO. But CG is x, therefore FO must be also equal to x. Likewise, according to the same rule, in the same left angle CGOF, side CF must be equal to the opposite side GO, but CF is x, therefore GO must be also equal to x. So actually found out that quadrilateral CGFO is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other. Each side of this square is equal to x. In the next step, we will join points O and C together by a straight line. By joining points O and C, we can get there the right triangle CFO. So in the next step, I'll copy the right triangle CFO in a new page and we will implement the Pythagoras theorem on this right triangle CFO. Here by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The right triangle CFO is actually also an isosceles triangle because CF equals to FO. So CF equals to x and FO also equals to x. The hypotenuse is the missing side. So actually, this is the right triangle CFO that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle CFO, CO squared, that is the square of the hypotenuse, must be equal to CF squared plus FO squared. So I write it down. So in the right triangle CFO, CFO squared, CO squared, the square of the hypotenuse, equals to CF squared plus FO squared. CO is the missing side, so we leave it as it is. So CO squared equals to CF squared. CF is x, therefore CF squared is x squared plus FO squared. FO is also x, therefore FO squared is x squared. So in total, CO squared equals to x squared plus x squared, that is 2x squared. So if we found out that CO squared equals to 2x squared. Here we take a root out of this equation, and finally we get that the missing side, the hypotenuse CO, is equals to the square root of 2 times x units in its length. So if we found out that this is the missing side CO is equals to the square root of 2 times x units in its length. So here we can actually implement rule 7 in our drawing. Why? Because in our drawing, point O is the center of the big quarter circle. So from the center of the big quarter circle, we have line segment OC, and this line segment OC bisect chord ED. Again, line segment OC bisect chord ED. And line segment OC exits from point O, that is the center of this quarter circle. So in the drawing, we have actually line segment OC, that is from the center of the quarter circle, that bisect chord ED. Why it bisects chord ED? Well, because we know that EC equals to CD equals to X. And whenever you have from the center of the circle or quarter circle any line segment that bisects a chord, you can implement rule 7. So I'll repeat quickly on rule 7. According to rule 7, if a line segment is drawn from the center of a circle and bisect a chord, then the line segments will be also perpendicular to that chord. So in the drawing we have a circle, point O is the center of the circle, and we have line segment OM that bisects chord AB. That is to say, AM equals to MB, and therefore line segment OM bisects chord AB. And because of the fact that OM bisects chord AB, OM also will be perpendicular to AB. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 7. So I can actually implement rule 7 in our drawing. Why? Because in our drawing, we have, if we relate to the quarter circle, the center of the quarter circle is here at point O. So from the center of the quarter circle, we have line segment OC that bisects chord ED. That is to say, it divides chord ED into two halves. Each half equals to X. Therefore, we can implement here rule 7. All the requirements of rule 7 are satisfied, and therefore we can implement here rule 7. According to rule 7, line segment OC also is perpendicular to chord ED. If line segment OC is perpendicular to ED, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 7. So OC is perpendicular to DE. In the next step, we join points O and D together by a straight line. What is the definition of line segment OD? Line segment OD starts from point O, that is the center of the quarter circle, and ends at point D, that is the point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, OD is the radius of the quarter circle, and we know that the radius of the quarter circle equals to 5 units. Therefore, OD equals to 5. In the next step, I'll copy the right green triangle CDO in a new page, and we will implement the Pythagoras theorem on this right green triangle CDO. Here by PT is the progression from Pythagoras theorem. So actually, this is the right green triangle CDO that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle CDO, the O squared, that is the square of the hypotenuse, equals to CD squared plus CO squared. So I'll write it down. The O squared, that is the square of the hypotenuse, equals to CD squared plus CO squared. DO, the hypotenuse DO equals to 5, therefore DO squared is 5 squared, that is 25. And it is equals to CD squared. CD is x, therefore CD squared is x squared plus CO squared. CO is square root of 2x, therefore CO squared is square root of 2x squared, that is actually 2x squared. So in total, we have found out that 25 equals to x squared plus 2x squared. X squared plus 2x squared equals to 3x squared. So 25 equals to 3x squared. We will divide this equation by 3. And finally we get that x squared equals to 25 over 3. X squared equals to 25 over 3. Our mission is to find out the area of this semicircle that is inside this quarter circle. What is the area of the semicircle? The area of the semicircle equals to the area of the circle over 2. And the area of the circle is pi times the radius squared. The area of the circle is pi times the radius squared. And the radius is x, therefore it is pi x squared. If the area of the circle is pi x squared, it means the area of the semicircle will be equal to pi x squared over 2. So the area of the semicircle is equals to pi x squared over 2. So it is pi over 2, and x squared is 25 over 3. Therefore, we substitute x squared in this equation by 25 over 3. So in total, we found out that the area of the semicircle equals to 25 pi over 2 times 3 is 6. So it is 25 pi over 6 square units. Or in terms of numbers, it is equals to 13.09 square units. Repeat again, we have found out that the area of this semicircle that is inside the quarter circle A or B, the area of the semicircle equals to either 25 pi over 6 square units, or in terms of numbers, it is equals to 13.09 square units. We finished with the first question. In the next step, we present you the second question, and we answer on the second question. So in the drawing, we have a rectangle ABCD. Inside this rectangle ABCD, we have this quarter circle. PBC is a quarter circle. And we also have a semicircle. This is a semicircle. Again, our mission is to find out the area of this green shape. Okay, and we know that side AB equals to 5 units in its length. AB equals to 5 units in its length. So we know that ABCD is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC, but AB is 5, therefore DC must be also equal to 5 units in its length. So DC equals to 5 units in its length. DC equals to 5. We define the center of this semicircle, this point is point O. We'll define the touching point of this semicircle with this quarter circle. This point is point S. We know that ABCD is a rectangle, and we also know that all the angles inside any rectangle are right angles. Therefore, this is angle ADC, that is a right angle. So in the drawing, we have an external notch between this semicircle and this quarter circle. That is to say, they touch each other externally at this point, point S. And whenever you have an external notch between two circles or semicircles, you can implement rule 10. So I'll repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, that is to say they have an external notch between them, then the straight line that connects their centers together passes through their touching point. So in the drawing we have two circles. Those two circles have an external notch between them at this point, point P. That is to say they touch each other externally at point P. The center of this circle is here at point M. The center of this circle is here at point O. And the straight line that connects the centers together is of course the straight line OM. And according to this rule, rule 10, the straight line OM passes from point P, that is their touching point. Again, according to rule 10, this rule 10, the straight line OM passes from point P, that is their touching point. Or OPM is one straight line. Again, according to rule 10, OPM is one straight line. So actually, we can implement rule 10 in our drawing. Why? Because in our drawing, as I mentioned before, we have an external notch between this semicircle and this quarter circle. That is to say, they touch each other externally at point S. Therefore, we can implement here rule 10. The center of this semicircle is here at point O. The center of this quarter circle is here at point C. And the straight line that connects their centers together is of course the straight line OC. And according to rule 10, the straight line OC must pass through point S, that is their touching point. Again, according to rule 10, the straight line OC must pass through point S, that is their touching point. So we connect points O and C together by a straight line, and the straight line OC must pass through point S, that is their touching point, according to rule 10. So it is very easy to see that indeed the straight line OC that connects the centers together passes through point S, that is their touching point. Or in other words, OSC is one straight line. Again, according to rule 10, OSC is one straight line. So if OSC is one straight line, it means that OC will be equal to OS plus SC. Again, OC equals to OS plus SC. So I write it down. OC equals to OS plus SC. Why? Because of the fact that OSC is one straight line, according to rule 10. So OC, what is the so OC equals to OS. What is the definition of line segment OS? Line segment OS starts from point O, that is the center of the semicircle, and ends at point S, that is the point on the semicircle itself. So this is exactly the definition of a radius. Therefore, OS is the radius of this semicircle. So first of all, we will define the radius of the quarter circle BC as x. So BC is the radius of the quarter circle, that is equals to x according to our definition. But the radius of the quarter circle is actually it is actually the diameter of this semicircle. Again, the radius of this quarter circle is the diameter of this semicircle. So we know that the diameter of this semicircle, the diameter AD equals to x. Why? Because according to the rule, that the opposite sides of rectangle are equal to each other. So in rectangle ABCD, side BC must be equal to the opposite side AD. But BC equals to x, therefore AD must be also equal to x. AD is the diameter of the quarter circle and it's equals to x. If the diameter AD equals to x, the radius must be equal to half of it. So the radius AO must be equal to x over 2, and the radius OD must be also equal to x over 2. Likewise, OS is also the radius of the quarter circle, and therefore it is equal to x over 2. What is the definition of line segment SC? Point C is the center of the quarter circle. Point S is the point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, CS is the radius of this quarter circle that is equal to x according to our definition. Therefore, CS equals to x. So we already found out that OS equals to S, OC equals to OS plus SC. So OC equals to OS, that is x over 2, plus SC, and SC is x. So in total, OC equals to x over 2 plus x. X over 2 plus x is 1.5x, so 3 over 2x. So in conclusion, we found out that the length of line segment OC, in total, it is equal to 3 over 2x. 3 over 2x units in its length. In the next step, I will copy the right triangle DOC in a new page and we'll implement the Pythagoras theorem in this right triangle DOC. Side DC equals to 5 units, and we just right now found out that the length of the hypotenuse OC is 3 over 2x units. Here by PT is the dimension of Pythagoras theorem. So actually, this is the right triangle ODC that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle ODC, OC square equals to OD square plus DC square. So I write it down. OC square, that is the square of the hypotenuse, equals to OD square plus DC square. OC equals to 3 over 2x units in its length, therefore OC square equals to 3 over 2x squared. 3 over 2x squared equals to 9 over 4x squared. And it is equals to OD square. OD is x over 2, therefore OD square is x over 2 squared. That is x squared over 4 plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in conclusion, we should find out that 9 quarters x squared equals to 1 quarter x squared plus 25. Here we subtract x squared over 4 from this equation, and we get that 9 quarters minus 1 quarter, 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared, that equals to 25. 8 over 2, 8 over 4 is 2, so in total this expression will be equal to 2x squared. So if we found out that 2x squared equals to 25. Here we'll divide this equation by 2 and finally we get that x squared equals to 25 over 2. X squared equals to 25 over 2. So here we take a root out of this equation and finally we get that x equals to the square root of 25 over square root of 2. The square root of 25 is 5 over square root of 2. So x equals to 5 over square root of 2. And x squared equals to 25 over 2. Our mission is to find out the area of this green shape. What is the area of the green shape? The area of the green shape, from the domain, it is very easy to see that the area of the green shape, in total, it will be equal to the area of rectangle ABCD minus the area of this semicircle minus the area of this quarter circle. So I repeat again, we actually found out that the area of the quarter circle, the area of the green shape, the area of the green shape equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. So what is the area of rectangle ABCD? The area of any rectangle equals to the length of the rectangle times the width. The length is x and the width is 5. So in total, the area of rectangle ABCD is 5x. Minus the area of the semicircle. What is the area of the semicircle? The area of the semicircle is the area of the circle over 2. The area of the circle is pi times the radius squared. So it is pi times the radius is x over 2 squared. So it is x over 2 squared. That is the area of the circle. And the area of the circle, the area of the semicircle will be equal to the area of the circle over 2. So we divide the area of the semicircle, that is pi times x squared, pi times x over 2 squared by 2. This way we get the area of the semicircle minus the area of the quarter circle. The area of this quarter circle equals to the area of the circle over 4. The radius of the circle is x. Therefore, the area of the circle is pi x squared. And the area of the semicircle will be equal to the area of the circle over 4. So it is pi x squared over 4. So in total, we found out that the area of the green shape equals to 5x minus pi x squared minus pi times x over 2 squared divided by 2 minus pi x squared over 4. And here we have 5x. We'll open the brackets here. It will be equal pi times x over 2 squared is pi minus pi x squared over 4 divided by 2 minus pi x squared over 4. So here we have 5x minus pi x squared divided in the denominator we have 2 times 4, that is 8. So in total this expression equals to pi x squared over 8 minus pi x squared over 4. Here we'll multiply this expression by 2 and then we will divide it by 2 in order to have a common factor with this expression. So it will be equal to 2 pi x squared over 8. So in total, we found out that the area of the green shape equals to 5x minus pi x squared minus 2 pi x minus pi x squared over 8 minus 2 pi x squared over 8 is minus 3 pi x squared over 8. So in total, the area of the green shape will be equal to 5x minus 3 pi x squared over 8. And we have already found out that x equals to 5 over square root of 2 and x squared equals to 25 over 2. Therefore, we can substitute x in this equation by 5 over square root of 2 and x squared in this expression by 25 over 2. We'll do it now and we get that 5x is 5 times 5 over square root of 2 minus 3 pi over 8 times x squared, and x squared equals to 25 over 2. So in total, we actually found out that the area of the green shape equals to 5 times 5 is 25, so in total this expression equals to 25 over square root of 2 minus, we have in the numerator of this expression 3 pi times 25 is 75 pi divided by, in the denominator we have 2 times 2, that 8 times 2, that is 16. So in total we actually found out that the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16. Actually, in terms of numbers, the value of this expression in total is equals to 2.95 square units. And that is the answer to the question. I'll repeat again. We actually found out that the area of this green shape is equals to 2.95 square units. Okay. So in the next step, I will summarize the lecture. We start with the first question, of course. In the first question, we found out the area of this semicircle that is located inside this quarter circle A or B. So in the drawing, we have a quarter circle A or B. We know that AO equals to 5 units in its length. That is to say, the radius of this quarter circle is 5, and point O is the center of the quarter circle. So inside this quarter circle, we have this semicircle, and our mission is to find out the area of this semicircle. So first of all, we define the center of this semicircle. This point is point C. And here we define the radius of this semicircle as x. Therefore, CD equals to CE equals to x. The above the radii of this semicircle is equal to x according to our definition. And then we defined the point of tendency of tangent BO with this semicircle as point F. We defined the point of tendency of tangent AO with this semicircle, this point as point G. Then we join point C and F together by straight line. CF is of course the radius of this semicircle that is equals to x according to our definition. Here we have the radius CF that is drawn to point F, that is the point of tendency of tangent BO with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent BO will be perpendicular to the radius FC. If BO is perpendicular to FC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join point C and G together by straight line. CG is of course the radius of this semicircle, that is equal to x. Here we can implement also rule 1 because we have the radius CG that is drawn to point G, that is the point of tendency of tangent AD with this semicircle. Whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius GC. If AD is perpendicular to GC, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. The same rule 1. By doing these constructions, we can do quadrilateral CGOF. Inside quadrilateral CGOF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral CGFO, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be a rectangle if not a square. So we relate to quadrilateral CGOF as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle CGOF, side CG must be equal to the opposite side FO, but CG is x, therefore FO must be also equal to x. Likewise, according to the same rule, in the same rectangle CGFO, side CF must be equal to the opposite side GO, but CF is x, therefore the opposite side GO must be also equal to x. In conclusion, actually found out that quadrilateral CGFO is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Each side of this square is equal to x. Okay. So we join point C and O together by straight line. By joining point C and O, we create the right triangle, triangle CFO. It is a right and associated triangle, triangle CFO. So I copied the right and associated triangle CFO in a new page, and we implemented the Pythagoras theorem with this right triangle CFO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the sides of the perpendiculars. So this is the right triangle CFO that I copied from the original domain. According to the Pythagoras theorem, this right triangle CFO, CO square equals to CF square plus FO square. Again, CO square equals to CF square plus FO square. CO is the missing side, so we leave it as it is. So CO square equals to CF square. CF is x, therefore CF square is x square plus FO square. FO is also x, therefore FO square is x square. So in total, we actually found out that CO square equals to x square plus x square. X square plus x square is 2x square. So CO square equals to 2x square. Here we divided this, we took a root out of this equation and finally found out that CO, the length of the hypotenuse CO, is equal to the square root of 2 times x units. So we actually found out that the length of this line segment CO is square root of 2 times x units. So actually we know that point O is the center of this quarter circle. So from the center of the quarter circle, that is to say from point O, we have line segment OC that bisect chord DE. And whenever you have from the center of the circle any line segment that bisect the chord, you can implement rule 7. So I'll repeat quickly on rule 7. According to rule 7, if a line segment is drawn from the center of a circle and bisect a chord, then the line segment will be also perpendicular to that chord. So we have here a circle. This is point O, that is the center of this circle, and we have also line segment OM that bisect chord AB. That is to say, AM equals to MB. And because of the fact that line segment OM bisect chord AB, line segment OM will be also perpendicular to chord AB. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule, rule 7. So we can actually implement rule 7 in our drawing. Why? Because in our drawing, we have from the center of this quarter circle, that is to say from point O, we have line segment OC that bisect chord ED. That is to say, CE equals to CD equals to X. So it divides chord DE into 2 halves. And whenever you have such a reality that from the center of the circle, we have a line segment that bisects a chord, then that line segment will be also perpendicular to that chord according to rule 7. Therefore, line segment OC will be also perpendicular to chord DE. If OC is perpendicular to DE, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 7. In the next step, I copied the right green triangle DCO in a new page and implemented the Pythagoras theorem on this right triangle DCO. So actually, this is the right triangle CDO or DCO that are coming from the original domain. Here we have CD is the radius of this semicircle that is equal to x according to our definition. We actually joined points O and D together by straight line. What is the definition of line segment OD? Line segment OD starts from point O, that is the center of the quarter circle, and that's at point D, that is the point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, OD is the radius of this quarter circle, and the radius of the quarter circle equals to 5, because AO equals to 5. So DO is the radius of the quarter circle, that is equals to 5. DO is also the hypotenuse of this right hand triangle DOB. We have already found out that CO equals to the square root of 2 times x, and CD is the radius of the quarter circle, that is x. So actually, this is the right hand triangle CDO that according to the original domain. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares from the perpendiculars. That is to say, here it means that OD square equals to CD square plus CO square. Again, DO square equals to CD square plus CO square. DO is 5, therefore DO square is 5 squared, that is 25, and it is equals to CD square. CD is x, therefore CD square is x squared, plus CO square. CO is square root of 2 times x, therefore CO square is square root of 2 times x squared, that is 2x squared. So in total, we found out that 25 equals to x squared plus 2x squared. X squared plus 2x squared is 3x squared. So in total, we found out that 25 equals to 3x squared. Here we divided this equation by 3 and finally found out that x squared equals to 25 over 3. X squared equals to 25 over 3. Our mission is to find out the area of this semicircle. The area of any semicircle equals to the area of the circle over 2. The area of the circle is pi times the radius squared, and therefore the area of the semicircle will be equal to pi times the radius squared over 2. And the radius of this semicircle is x, therefore the area of the semicircle will be equal to pi x squared over 2. So the area of the semicircle equals to pi x squared over 2. So it is pi over 2 times x squared. And we just right now found out that x squared equals to 25 over 3. Therefore, we can substitute x squared in this equation by 25 over 3. We did it and actually found out that the area of the semicircle equals to pi over 2 times 25 over 3. Or 25 pi and 2 times 3 is 6. So it is 25 pi over 6 square units. Or in terms of numbers, it is equals to 13.09 square units. Repeat again. We actually found out that the area of this semicircle equals to either 25 pi over 6 square units, or in terms of numbers, it is equals to 13.09 square units. We finished with the first question. And actually presented to you the second question. We solved the second question. So our mission is in the second question is to find out the area of this green shape. So in the drawing we have rectangle ABCD. We know that AB equals to 5 units in its length. In addition, inside this rectangle ABCD we have this semicircle and this quarter circle. They touch each other at point S. Again, our mission is to find out the area of this green shape. So first of all, we know that all the angles inside the rectangle are right angles, so this is a right angle. And we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC, but AB is 5, therefore DC must be also equal to 5. Here we defined the radius of the quarter circle as x. Therefore BC is the radius of the quarter circle, is equals to x according to our definition. We know that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side BC must be equal to the opposite side AD. But BC is x, therefore AD is also x. But AD is also the diameter of the semicircle. So we actually found out that the diameter of this semicircle equals to x. If the diameter is x, it means that the radius must be equal to half of it. That is to say, the radius of this semicircle equals to x over 2. So OA is the radius of the semicircle, that is x over 2. OD is also the radius of this semicircle, that is x over 2. We have here an external notch between this semicircle and this quarter circle, that is to say, they touch each other externally, this point S. And whenever you have an external notch between two circles or semicircles, you can implement rule 10. So I repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching points. So in the drawing we have two circles and they have an external notch between them at point P. That is to say they touch each other externally at point P. The center of this circle is here at point M. The center of this circle is here at point O. And the straight line that connects the centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through point P, that is their touching point. Again, the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, OPM is one straight line. So we can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external notch between this semicircle and this quarter circle. That is to say, they touch each other externally at point S. Therefore, we can implement here rule 10. According to rule 10, the straight line that connects the centers together. What is the straight line that connects the centers together? The center of this circle is at point O. The center of the quarter circle is at point C. And the straight line that connects the centers together is of course the straight line OC. And according to rule 10, the straight line OC must pass through point S, that is their touching point. Again, the straight line OC must pass through point S, that is their touching point. Or OSC is one straight line. Again, OSC is one straight line. And because of the fact that OSC is one straight line, it means that OC will be equal to OS plus SC. Again, OC equals to OS plus SC. OS is the radius of this semicircle, that is equal to x over 2. SC is the radius of this quarter circle, that is equal to x according to our definition. So in total, OSC or OC will be equal to x over 2 plus x. Again, OC equals to OS, that is x over 2, plus SC, that is x. So in total, OC equals to x over 2 plus x. X over 2 plus x equals to 1.5x or 3 over 2x. So if we found out that OC equals to 3 over 2x units in its length. In the next step, I copied the right triangle ODC in a new page, and we implemented the Pythagoras theorem on this right triangle ODC. Again, the opposite OC equals to 1.5x or 3 over 2x. OD is x over 2, and according to the rule that the opposite sides of a rectangle are equal to each other, we get that in the rectangle ABCD, side AB must be equal to the opposite side DC. But AB is 5, therefore DC must be also equal to 5. So I copied the right triangle ODC in the new page and we implemented the Pythagoras theorem on this right triangle ODC. So actually, this is the right triangle ODC that they copied from the original drawing. Again, OD equals to x over 2, DC equals to 5, and the opposite OC equals to 3 over 2x. According to the Pythagoras theorem, and this right triangle ODC, OC squared equals to OD squared plus DC squared. OC is 3 over 2x, therefore OC squared is 3 over 2x squared. That is actually 9 over 4x squared plus OD squared. OD is x over 2, therefore OD squared is x over 2 squared, that is x squared over 4 plus DC squared. DC is 5, therefore DC squared is 5 squared, that is 25. So in total we found out that 9 quarters x squared equals to 1 quarters x squared plus 25. Here we subtracted x squared over 4 from this equation and found out that 9 quarters x squared minus 1 quarter x squared equals to 8 quarters x squared. This equals to 25. 8 over 4 is 2, so in total this expression equals to 2x squared. So if we found out that 2x squared equals to 25, we divided this equation by 2, and finally found out that x squared equals to 25 over 2. We took out of this equation and finally found out that x equals to the square root of 25 over 2. The square root of 25 is 5 divided by square root of 2. So in total x equals to 5 over square root of 2 and x squared equals to 25 over 2. Our mission is to find out the area of this grain shape. What is the area of the grain shape? From the drawing it is very easy to see. The area of this grain shape equals to the area of the rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. Repeat again. The area of the grain shape in total equals to the area of rectangle ABCD minus the area of the semicircle minus the area of the quarter circle. What is the area of rectangle ABCD? The area of rectangle ABCD is the area of any rectangle is the width times the length. The width is x, the length is 5, so in total it is 5x. And again, the area of rectangle ABCD is 5x. Minus the area of the semicircle. The area of this semicircle equals to the area of the circle over 2. The radius is x, therefore the area of the circle is pi. The radius is x over 2. Therefore the area of the circle is pi times x over 2 squared. And the area of the semicircle, we divide the area of the circle by 2. So it is pi x over 2 squared divided by 2. So total we found out the area of the semicircle equals to pi x squared, pi times x over 2 squared divided by 2, minus the area of this quarter circle. The area of the quarter circle equals to the area of the circle over 4. The radius of this circle is x, therefore the area of the circle is pi x squared. And the area of the quarter circle will be equal to pi x squared over 4. And again, the area of the quarter circle equals to pi x squared over 4. So here, actually found out, the value of this expression in total is equal to the area of the grain shape. So it is 5x. Here we have pi times x over 2 squared divided by 2. X over 2 squared is x squared over 4 divided by 2. Minus pi x squared over 4. So we have here in the denominator 2 times 4, that is 8. So in total this expression will be equal to 5x minus pi x squared over 8. Here we multiplied this expression, the numerator of this expression by 2 and the denominator by 2 in order to have a common factor with this expression. So after we multiply it by 2, it will be equal to 2 pi x squared over 8. So in total, the area of the grain shape equals to 5x minus pi x squared over 8 minus 2 pi x squared over 8. So it is 5x and pi x squared over 8 minus 2 pi x squared minus pi x squared over 8 minus 2 pi x squared over 8 equals to minus 3 pi x squared over 8. So in total, the area of the grain shape equals to 5x minus 3 pi x squared over 8. So here we have already found out that x equals to 5 over square root of 2 and x squared equals to 25 over 2. So we can actually substitute x in this expression by 5 over square root of 2 and x squared in this expression by 25 over 2. We did it And we found out that the area of the green shape in total equals to 5 times 5 over square root of 2 minus 3 pi over 8 times 25 over 2. 5 times 5 is 25, so in total this expression equals to 25 over square root of 2. And here we have 3 pi times 25 is 75 pi divided by 8 times 2 is 16. So it is 75 pi divided by 16. So we found out that in total the area of the green shape equals to 25 over square root of 2 minus 75 pi over 16 square units, or in terms of numbers, the area of this green shape equals to 2.95 square units. Okay, thank you very much.